Hello everyone, welcome to lecture 15. So today we will be looking at changing the composition and trying to look at phase diagrams or how the various phases evolve. So far if you remember, we were looking at changing the pressure, changing the temperature. We have created the P versus T phase diagrams. We have actually looked at how these phase boundaries come up. We have derived them using the Clausius-Clapeyron equation and so on. So if I go back to writing what dg is, right. So dg is, it depends on T, it depends on P, but it also depends on N, right. So this is so it is S dt, V dp and mu dn, right. So minus S dt I think plus V dp and plus mu I d n I, right. So that is what dg is. So we have changed temperature, we have changed pressure, we have changed both temperature and pressure simultaneously, saw how G evolves between two different phases, and based on that we have said that okay, this phase wins at this temperature pressure, this phase wins at this temperature pressure. So we have created, by looking at G as a proxy, by looking at minimal G gives me the stable phase, right. So by looking at this as the criterion, we have said all right, so by changing we have created the P and T phase diagrams, which means at what pressure and temperature which phase wins globally, right. So which phase wins the war of thermodynamics, right. So which phase is most stable phase, right. So that's, those are the sort of diagrams we have created so far, right. So but the other important thing is changing N, right. So with changing N in an open system, right. So this is what is useful for material synthesis, that is what we said, and so how does that change the G, and so how does that reflect in which phase wins and which phase does not win. Okay. So that is the exercise that we are going to do, and all this comes under the purview of what is called solution thermodynamics. Okay. So we are going to create solutions, and we are going to see add some atoms, remove some atoms from already existing phases, and see how these phases react to that, and see if they can create new phases, right. So just by adding some atoms and removing some atoms. Okay. All right. So before that, so let us give some definitions, so that are quite useful for solution thermodynamics. Now I have a phase alpha. Now alphas and betas are my phases. Like I said, 1 and 2 are components, right. So alpha, beta, gamma, delta, these are all what are called the phases, right. So it can be some crystals, so any phase, right. So the way we define a phase has a different crystal structure, let us say. Okay. So or a different order parameter to be more physics wise correct, but let us be a bit vague and say something with a different crystal structure is a different phase. Gas has a different structure, right. Liquid has a different structure. So liquids and gases are different phases, correct. Now solid in iron in what is called a face centered cubic structure is a different phase. Iron in a body centered cubic structure is a different phase, right. So the structure is a proxy for a phase for us, right. So the structure defines what phase is initially at least, and then so if necessary we will say that okay, we can have phases of same structure, but some other order parameter changes. So those are slightly more complex phase diagrams, but initially for now, if there is a phase change, there is a structure change, right, and associated with the structure change there is a volume change, there is an enthalpy change, and all these things. Okay. So I am going to represent all these phases as alpha, beta, gamma, delta, all the Greek alphabets, all the Greek letters, right. So in the Greek alphabet, so I am going to represent, now these phases can have multiple components, right. So like I said earlier, platinum palladium, I can mix platinum and palladium and create one FCC material, right, in some proportions, right. So, how much platinum is there, how much palladium is there, right. So, platinum is component 1, palladium is component 2 in this example, and component 3, component 4. So, these actually represent the components in phases, right. So, I have all these components are coming together, mixing together to form certain phases, and phase is determined by the crystal structure. So, that is the distinction between alpha, beta, gamma. I will keep on using this terminology, right, but so it is important for you to realize that when I say mu alpha of 1, right, something like this. So, this means this is the chemical potential of species 1 in the phase alpha, right. So, this is the chemical potential of species 1 in the phase alpha. Now, phase alpha can have a species 2, it can have a species 3, right, it can have platinum, it can have palladium, it can have magnesium, whatever, right. But just the act of adding one more platinum, how much bond energy is it going to create, right. So, how much energy is it going to give out, right, that defines my mu 1 of alpha, mu 1 of alpha. Now, mu 2 of alpha is different, I have to add palladium atom now to this solid solution of platinum, palladium, magnesium, or whatever it is. Okay. Okay, so that's so this is going to be the nomenclature from now on, and we are going to further develop the language of this chemical potential, and so because we are going moving towards systems where there is going to be exchange of atoms. Okay. Okay. Now alpha transforms to beta, right, without any change in composition, right. So, alpha is let us say platinum, palladium 0.5, 0.5, beta is also platinum, palladium 0.5, 0.5, alpha is in an FCC structure, beta is somehow I made it into a BCC structure, right. So, there is no change in composition, right, just like water transforms from ice to H2O transforming into water, right. So, there is no change in composition, right. So, all the n molecules of ice have transformed into n molecules of water. Okay. Okay, so this is still not an open system, there is still no mass exchange, so but the entire phase is the entire n molecules of water has transformed to n molecules of ice or vice versa, right, and these sort of transformations are called congruent transformations, the easiest phase transformations. Right. So, essentially what we are saying is, look, I have alpha going to beta, so I said I will change the number of, I will add atoms, I will remove atoms and then see how things happen. But the simplest case is not adding atoms, not removing atoms, right. So, we are back to square one, and these are congruent transformations where at a particular temperature or a particular pressure alpha changes to beta, right. So, at the without a change in composition, right. Okay, good. So, these are what are called congruent phase transformations, right. All right. Now, however, the slightly more complex phase transitions where there is a change in composition is alpha giving rise to beta plus gamma, right. So, this is a phase transition in which composition changes. Now, so first of all we need to understand what I mean by the word composition, right, composition, concentration, all these things, right, and further then I have to understand these kinds of phase transitions, I have to develop the language of chemical potential. Okay. So, let us say I have n total number of atoms or molecules in my system, and that n comes from species 1 and species 2. Right, it is species 1 and species 2 that are making alpha phase, that are making beta phase, that are making gamma phase. Okay. Now, typically, right, so we are looking at what is called solution thermodynamics. So, I have a solute and I have a solvent, right. Solute is something which is less in concentration, solvent is something which is more in concentration. Okay. And from here on we are going to look at something like x1, x1 is the atomic fraction or mole fraction, right, is equal to n1 by n. Right. So, this is the units in which we are going to dictate how concentration is going to change, right, or how the composition, not weight fractions, we are going to look at atomic fractions or mole fractions. Okay. So, x2 is equal to n2 by n, okay, and we have this thing called x1 plus x2 equal to 1. Okay. So, now instead of saying that, oh, I am adding more molecules, I am subtracting some molecules, right. So, I want to do this in some sort of a normalized scale, right. So, the total concentration or total atomic fraction of all the atoms combined together is 1. Okay. So, that is what I am going to say, the total atomic fraction of all the atoms combined together, all the species should be 1, that is my normalizing factor. Okay. And so, I can independently then change x1, x2, right. So, I can have more mass, I don't mind that, but the variables that I am going to change are x1, x2, x3 and so on and so forth. So, these are the atomic fractions. Okay. So, when I say composition, when I say concentration, I am actually changing these things, right. So, x1, x2, x3, these are the things I am going to change. Okay. These are the atomic fractions and or mole fractions. They are all related by sigma xi equal to 1. Okay. Now, if I have only 2 species, what does changing composition mean? Changing composition means I have so I have x1 and x2, but x1 plus x2 equal to 1. So, I have only one independent variable, right, and that is x2. Okay. So, I mean I am going to by default I am going to take the independent variable as x2, right. So, then I have so all these parameters that depend on x2, x2 is the atomic fraction of species 2. Okay. So, this is assuming that the total number of molecules, right. So, there is going to be a so if I have a phase alpha, right. So, this is all phase alpha that has converted from beta and gamma, right. So, this is the phase transition that I am looking at. Alpha altogether has n molecules is n1 plus n2, right. Now, beta and gamma together should have n molecules again, right. So, there is going to be some exchange of molecules between alpha, beta and gamma. So, when alpha converts to beta and gamma, right. So, alpha gives away some molecules to beta and taking away some molecules from gamma, that sort of a thing. There is going to be some redistribution of atoms, right, but the total number of atoms is going to be the same, and hence so it makes sense that we look at so n1 by n sort of quantity, right, or n2 by n sort of quantity. So, these are my x1s and x2. So, it makes sense to look at atomic fractions because the total number of molecules by mass conservation, right. So, I can exchange them between various phases, but the total number of molecules is the same, right. Now, if beta is my phase of interest or if beta is my system, then so that system is an open system because it is taking molecules from it is taking atoms from gamma, it is giving back atoms from alpha and so on and so forth, right. So, all these things are happening, but so overall if I consider alpha, beta, gamma, the total number of molecules are going to be the same. Okay. All right. So, having said that, okay, so how does this phase transition happen? So, let us say alpha is a phase where I have x1 is my solute is 0.3 and x2 is 0.7. Okay. Now, alpha transforms to beta plus gamma at some pressure, some temperature, right. Now, beta is a phase which is so alpha is rich in 2. Okay. Now, beta is a phase that turns out to be rich in 1. Okay. So, beta has some fraction which is so it has 0.6 of 1, 0.4 of 2. Okay. And gamma is another phase. So, essentially what does this phase transition mean? This phase transition means initially I am starting with a homogeneous sphere of alpha. What does the homogeneous sphere of alpha mean? Homogeneous region of alpha. Initial condition, which means wherever I pick, right. So, which means, you know, so if I look at the composition anywhere on this, you know, phase diagram, you know, so wherever I pick, right. So, x2, right. So, if I am looking at x2 at whichever location, right. So, R tells me the location, right, x2 at whichever location. Now, that x2 is 0.3. So, wherever I see in this alpha, x2 is 0.3. So, x2 I can call it some kind of an order parameter. It is actually telling me, it is actually defining, just the value of x2 is defining which phase I have, right. If x2 is 0.3 everywhere, I am going to say that it is an alpha phase. Okay. Now, I mean, it is not a very proper order parameter according to physics, but you know, so x2, I am using x2 as a proxy to determine what is alpha, what is beta, what is gamma. Okay. Now, by changing some conditions, I have changed some temperature, pressure, right. Alpha, you know, becomes something like beta here and gamma here. Okay. So, F1 fraction of alpha has converted to beta, F2 fraction of alpha has converted to gamma. Okay. Now, you know, so beta is rich in 1, that means x2 in beta is equal to 0.4, right, that is what we said. Okay. So, I take this volume, and out of this volume, you know, so some fraction of it now has more species number 1, right. So, this has, you know, equal species, you know, so species x2 initially equal to 0.3, but now in this region, right. So, in region 1 x2 has become sorry, x2 will be 0.7, sorry, right. So, that is what we started with, x2 is 0.7. So, in this region x2 will have to come down from 0.7 to 0.3 or 0.4. Okay. Now, x2 is coming down from 0.7 to 0.4, which means you know, molecules, that the 2 atoms, right. So, 2 atoms are going to be these circles, right, red circles, or let me change the color of 2 atoms, right. Atom number 2 is some kind of a blue circle, right. So, these are the 2 atoms. Now, 2 atoms which were, you know, larger in composition now should have to move away from here, right. So, they have to move away, so that the net x2 becomes, x2 comes down from 0.7 0.4 after this phase transition, right. Now, where is this x2 going to? This is the beta phase, right, and all this x2 is going to the gamma phase, right, and in gamma phase takes more 2, right. So, in gamma phase x2 equal to, it goes to 0.9 or something like that. So, gamma is more rich in 2, right. So, than alpha and beta, right, and beta is richer in 1. Okay. So, what I did by doing this phase transition from alpha to beta plus gamma is I have now created 2 different or few different regions, right. So, one of which is 2 rich, or sorry 1 rich, and the second one is 2 rich. It does not need to be only 2 regions, right. So, I can have, you know, this is beta, this is gamma, this is beta again, this is gamma, you know. So, I can have different sort of splitting, right. So, wherever I write beta, that is 1 rich, wherever I write gamma, that is 2 rich, right. So, I have taken a homogeneous region in composition, which is alpha, and I have converted into inhomogeneous regions, inhomogeneous mixture of beta and gamma. So, this is what the phase transition looks like. And in the process, and how did this happen? If I ask the question, how did this happen? Right. So, we said in thermodynamics we do not ask this question actually comes from kinetics, right. So, let us still so ask the question, right. So, because nothing prevents us from asking the question. Okay. So, how did this happen? This happened because so there was some molecules of 2 that have started going to some so from some regions to some other regions. So, from region 1 to region 2. Okay. And this going from region 1 to region 2, this process is called diffusion or long range diffusion, right. So, whenever I have these compositional changes, I should have a long range diffusion, right. So, here it is long range diffusion of of 2, right. So, or 1, you can think that 1 has come from R2 to R1, right. So, this is so I have sort of made the solute here so the solute plus solvent, right. So, solute happens to be in region 1 so 2 is the solute, and in region 2 solute happens to be 1, right. So, that is the species of lower concentration. So, what I did is I did some solute partitioning, right. I have partitioned the solute into R1 and R2 or many regions, right. But this is what happens in compositional phase transitions, right. So, I start with a homogeneous entity, then I am going to split it up into set of inhomogeneous entities, right. So, alpha giving rise to beta plus gamma. These are non-congruent transformations, right. So, these are actually what are called non-congruent transformations, right. In a congruent transformation, alpha transforms to beta, right, but there is no there can be some diffusion, but so overall in beta the composition is exactly the same as alpha, right. So, that is a congruent transformation. In a non-congruent transformation, alpha transforms to beta plus gamma. I have to solute partition. Solute should move from alpha, so initially it is in alpha phase, but so some part, right. So, for example, region R1 here, right. So, x2 of R in the beta phase, now that becomes 0.4, but x2 at R in the gamma phase, whatever I have marked as gamma, right. So, this is beta, right. Now, that becomes 0.9. Okay. So, there needs to be some solute partitioning, or solute atoms should move around or diffuse around, right. So, this is the idea of diffusion, right. So, I am already introducing the idea of diffusion in phase transitions. This is very important. Atoms should move around for me to have this solution partitioning, right. So, I need to create enough conditions. If I freeze the atoms, if I arrest the atoms, if I do not give them enough temperature to move around, then they will not move, right. So, I have to let so the atoms realize, look, thermodynamically alpha you are not any so I will look at that very soon, but you are telling this phase that I have changed the conditions, I have tuned my conditions, right. So, the pressure and temperature such that thermodynamically alpha you are not the most stable phase here, it should be beta and gamma that are stable, right. Now, beta plus gamma you somehow mix yourself, so it is a mixture, right. So, you somehow find out regions that are supposed to be beta, that are supposed to be gamma, right. Now, how is it happening? How is this entire homogeneous phase trying to find out regions that are beta rich and gamma rich, or that are 2 rich and 1 rich, right. So, that is happening because 2 atoms, right. So, now because I am no longer thermodynamically stable, I should go towards some stable phase, and this going towards a stable phase or say stable set of phases is happening via diffusion, right. So, via long range diffusion, 2 is going from one region to another region, 1 is coming from one region to another region, right. So, diffusion is very important. You can see diffusion happen in many places, but diffusion turns out to be very important here. Okay. All right. So, that is the idea of what is called solution partitioning, right. Now, let us define certain things. So, now I understand what is this phase transition, what is meant by alpha giving rise to beta plus gamma inside a homogeneous material, right. So, some chunk is 2 rich, some chunk is 1 rich, and that is, since it is 2 rich, right. So, it cannot crystallize in an alpha phase, it has to go to some other phase now. That is what thermodynamics is saying at that volume and at that temperature and pressure, and so it goes to what is called a beta phase. Okay. So, when it is 1 rich, it has to go to some other phase, right. So, that turns out to be a gamma phase. Okay. All right. So, now let's write this so more mathematically, so that we will be able to do some some predictions of which phase is stable when so solute starts moving, when I put in some diffusion, right. So, into the problem. Okay. All right. So, for that I will start by defining small g. Okay. Now, small g is what is called average Gibbs free energy, and the way I define small g is just capital G by capital N. Capital N being the total number of molecules in the system being all phases included, right. So, at any given temperature, and G being just the free energy. Okay. So, free energy of all phases included. Okay. But so this includes so G will be a function of so it is function of temperature and pressure, that we know, but G is going to be a function of x2, right. It is not going to, so since I already wrote G is equal to G by N, right. So, G itself will not depend on N. It is not extensive by definition, right. So, capital G is an extensive property. If I increase the number of molecules, capital G will increase, but small g is only dependent on atomic fractions, right. So, small g only depends on atomic fractions, not the total number of molecules. So, it makes sense that we think about the small g's or the bulk free energies, as we are going to quickly transition into this language of what is called bulk free energies, but G small g is what we what is important for any sort of compositional phase diagrams that we are going to look at. Okay. And so capital G is given as N1 mu1 plus N2 mu2, this we have seen earlier, right. So, small g hence will be x1 mu1, but mu1 itself is a function of x2, right. So, now mu's so I have a mu1 and mu2, right. So, in a particular phase, right. So, this can be in an alpha phase, let us say, right. So, in any particular phase I have mu1 and mu2. So, this is a 2 species system. Okay. So, G alpha or so G at any phase is x1 times mu1 plus x2 times mu2, this is just by definition. Okay. Now, this is going to be super important from here on. Okay. So, G of x2, G just depends on x2, of course temperature and pressure, but at any given temperature and pressure, G of x2 is x1 times mu of x2 plus x2 times mu2 of x2. Okay. So, I will know G, which is the average free energy, if I know the composition x1 or x2 and chemical potentials of species 1 and chemical potential of species 2, right. Species 1 and species 2, species 1 and species 2 together form a solution, okay, of alpha. The solution has a phase alpha. Okay. So, that is how one needs to interpret it. Okay. Let us pause here, but let us quickly go back, because earlier I just forgot to do something, right. So, again let us go back to the idea of solute partitioning. This is something that I should have done earlier, but I just quickly forgot. So, let me do it before I move on any further. Okay. Now, solute partitioning, I said so alpha transforms into beta and gamma. Okay. So, the F1 of beta, F2 of gamma, right. So, F1 has a composition of x2 beta, F2 has a composition of x2 gamma, right, and alpha has a composition of x2 of alpha, right. Now, if I have to write a mass conservation, there should be mass conservation, right. Whatever species go from beta should go to gamma, right. So, the number of species, total number of 2 species should be constant, right. So, n times x 2 is a constant. So, any sort of partitioning should partition it in such a fashion. Okay. So, as a result you are actually going to get f 1 times x 2 of beta plus f 2 times x 2 of gamma. Now, that is equal to x 2 of alpha. So, this is what you have initially started with, this is just mass conservation. Okay. You have started with x 2, the fraction of 2 in alpha is x 2, right. The fraction of so x 2 and 2 molecules have gone away from beta and they have gone into gamma, right. So, gamma has become too rich, beta has become too poor, right. Now, how will it segregate? It will segregate based on the fractions, right. So, if I have f 1 times x 2 beta, f 2 times x 2 of gamma, that should be equal to the initial x 2 of alpha. Okay. Now, let us say f 1 is 0.3, right. So, just 0.3 of so 30% of the entire solid has become beta, and f 2 is 0.7, 70% has of the entire solid has become gamma, right. I said x 2 beta is 0.4, x 2 gamma is 0.9, right, and x 2 alpha is 0.7, right. So, I think now you can just plug in the numbers and say 0.7. Oh, sorry, I have to find something, I cannot give you everything, right. So, find the fractions, right, find f 1 and f 2, right. So, f 1 equal to 1 minus f 2, right. So, f 1 times 0.7, right, sorry 0.9 plus 1 minus f 1 times sorry, I am so sorry, just correct me. So, f 1 times x 2 beta is 0.4 plus 1 minus f 1 times 0.9, now that is equal to 0.7. So, I have 0.9 minus 2 f 1 sorry 0.9 plus 0.4. Now, what is that? That is 1.3 times f 1, that is equal to 0.7, right. So, these are simple problems that you can get in your gate or something like that. So, I have 0.2 is equal to 1.3 f 1, and so f 1 I can calculate it to be 0.2 divided by 1.3. This is nice, it is a number less than 1. So, good, hunky dory, right. So, so this will be the fraction of beta phase, right, and the fraction of gamma phase, that is 2 by 13. Okay, and fraction of gamma phase is going to be 11 by 13. Okay. So, that is how you solute partition, but once you solute partition and then you know that the compositions in each of these phases is so and so, that also determines the fraction of these phases, right. So the total amount of solid that has converted to gamma will be 11/13th, the total amount of solid that has converted to beta will be 2/13th, right. So, that is how you can estimate the fractions, right. So, or if I know the fractions I can estimate the compositions and so on. Okay. So, this is just mass conservation. Okay. So, mass conservation should be followed. Alright. So, now let us go back. So, let us go back and say that look yeah. So, mu 1 and mu 2, right. So, g of alpha sorry g of x 2 is x 1 times mu 1, which is a function of x 2, plus x 2 times mu 2, which is a function of x 2 again. Okay. Now, let us plot this g again after this slight digression, right. So, let us go back and plot g again. I have written g, right, is equal to mu 1 times x 1 plus mu 2 times x 2, right. Turns out if I plot this g as a function of x 2, now g as a function of x 2 is going to be so if I have a solution that should be formed, if a solution in the alpha phase forms, right. So, this is G in alpha phase, right. So, one of the phases, okay, as a function of x2 looks, you know, so these curves look concave down, right. So, these are these sort of functions that look you know, so that look like this, okay. So, with more, I mean, so essentially the way I am defining G of alpha phase depends on what is the x2, right. So, what is the x2, and if I have you know, pure alpha, the G is here. If I have if I have pure 1, so this is species 1, this is species 2, right, which means here x1 is 100%, x2 is 0. Here x2 is 1 and x1 equal to 0. So, that is how you read the phase diagram. This is composition, this is G, right. So, this is the G that we are going to plot from now on, okay. So, G looks this concave down, and that is when I know that a solution can form, and we will actually take up from here in the next class, okay. So, when G looks concave down, why are these, you know, sort of G versus composition curves, you know, how do they say that 1 and 2 are going to mix to form this phase, or 1 and 2 are not going to mix to form this phase, okay. So, but as a function of x2, if I fix my x2, I can read off my G, right. So, from these curves, and those curves actually come from G equal to x1 mu 1 x2 mu 1 plus x2 mu 2, right. So, if I plot this entire thing together, I will get a curve like this, okay. So, these are typically concave down curves, okay. All right. So, let us take it up take up from here in the next class, okay. Thank you.